think he has like one or two.
Okay, well, great pleasure, as these types of situations always are, but also a bit of sadness, because it also means the end of somebody's association with one's research group. But certainly it's a great pleasure to introduce our speaker today, Pavel Elkin. Pavel did his undergraduate studies in Russia, in Moscow, at the Mendeleev University of Science and Technology. During that time, he also spent a period, I guess a summer maybe, in the US, at University of Minnesota with Wayland Noland. And I think it was fortuitous that he did that, because probably made him aware of indole chemistry. He's an old school indole chemist. And after that, after he finished his undergraduate degrees, and I guess he also got a master's, he came to Chicago about 6 years ago and joined my group. And right from the beginning, I think he showed certain qualities that he continues to have, which is a love for chemistry, especially synthetic organic chemistry, and a real love for experimental aspect of it. This person, Pavel, just loves doing experiments, and he's always got lots of things going on in the lab. And needless to say, he's been extremely productive. He's worked on a variety of different projects. We're going to hear about, I think, maybe 3 of them, or maybe a little more than that, because I think it's hard for him to not include all the things he's worked on. But he's worked on, an area of chemistry that I personally love, which is orbital symmetry controlled reactions. And so starting out, he's worked on some things that I think were really exciting, but maybe not nearly as well developed and well understood. And so we shifted away from that. And then he moved into an area that also is close to my heart, Diels-Alder reaction. And we wanted to develop a class of dienes that would be enabling in a similar way that aminosiloxydienes became enabling, a class that really there was very little precedent for. And so he looked into developing these types of dienes, I think they're shown up there, to give a different group of cyclohexanones, differently substituted set of cyclohexanones, and explored the basic chemistry of it. And I think, as you'll see, that he's established these to be what should be useful dienes that hopefully will serve as useful tools in complex synthesis. And so he's looked at many different aspects of that work. And then more recently, he brings his own chair. Look at that. Then in connection with another project we were working on, we had the need for using an orbital symmetry control reaction, specifically a variation of a Claisen rearrangement, to solve a problem. And Pavel did some exploratory work in this area and found that it's actually a very powerful reaction, and has done a nice job developing that chemistry. And again, that comprises a major part of his thesis and his presentation, so you'll hear about that. Also thought about ways of using this rearrangement for complex molecule applications, and we sketched out a couple of applications, and as is typical of Pavel, rather than leaving it as conceptual, he was in the lab within a week trying the different ideas and has made considerable progress towards both of them. So look forward to hearing your presentation. It's been great having you in the group, and wish you continued success. Yeah.
Thank you so much, Professor Wang. Thank you so much for a kind presentation. Thank you all very much for coming. And again, thanks for the presentation, despite the fact that you kind of took everything interesting from my work, and now I don't have anything to present later. We've talked about everything, so. But as Professor Wang mentioned, in our lab, we significantly, I would say, after all these years, I would say they have a significant focus on the indole natural products, on the pericyclic reactions, specifically Diels-Alder reactions, and on the methodology in terms of development of a novel chiral acid catalysis and reduced acid catalysis and process acid catalysis. I was lucky enough to take part in, as Professor Rao said, in 2 of the main topics of our lab, and this was just fantastic for me. So over the course of my studies, I actually focused a lot on pericyclic reactions, as Professor Rao said, development of a novel Diels-Alder dienes for Diels-Alder reaction to construct 66 substituted cyclohexanones. and development of a new dearomative indole glycine arrangement and application of that to synthetic styles of the two different natural products, hemidentine and melanin. So, on the next slide, you can see a brief overview again of what I'm going to talk today. So, I'll focus a bit on the very first project that I had some success in this university, that is diel-south directions, and then I will continue to the next projects, development of free arrangements to access indolines in a nice and antiselective fashion. So, let's start. Let's get started. And we'll start with the very first project that actually succeeded in my hands here, hopefully. So, diel-south direction. Diel-south direction is one of the most fundamental reactions in organic synthesis. It was initially discovered in the early 1900s by Diels and Alder, described by them, and since then, because of its significantly important properties, that is very atom-economic reaction, it has a very high regio and stereoselectivity. It allows an easy access to the complex natural products, even in a chiral fashion if you start with chiral dienes or a chiral catalyst. Because of all these positive properties, it has found multiple applications in the total synthesis to date, and it still continues to be one of the most important and one of the most useful reactions in organic synthesis. The downside of the diel-south direction, at least the initial diel-south direction that was discovered by Diels-Alder and was further elaborated, is that for many examples it actually requires a lot of heat or a Lewis acid for the reaction to proceed efficiently. The field of use of the diel-south direction changed significantly when the group of Professor Danishevsky introduced so-called Danishevsky's dienes, doubly activated dienes for the synthesis of the natural products. The most improvement that was introduced to this diene is that the Danishevsky's diene, due to the two strong electron donating groups, is significantly higher reactive than normal unactivated dienes. It exhibits very high levels of regio and anti-selectivity, and it gives as a product the 4,4-disubstituted cyclohexanols that can be further transformed into useful cores for different natural products. In our lab, we discovered a modification of the Danishevsky's diene, the dimethylamina 3-siloxybutadiene, that proved to be significantly more active than Danishevsky's diene and exhibited significantly higher levels of regio and diastereoselectivities for the reactions. So, this discovery, along with overall usefulness of the diel-south direction in the synthesis, continued our interest in this reaction in our group. So, when we in general looked for the Danishevsky's diene, or on the diene we had the dimethylamine siloxybutadiene, we found that their use is very important. It has significant use in the synthesis. However, the downside of both of them, that they give access only to 4,4-disubstituted cyclohexanols to the best. However, many natural products exhibit the 6,6-disubstituted cyclohexanol motif, like acutopholone or velvetindorine C isothiocyanate. They all can be deduced to a 6,6-disubstituted cyclohexanol core structure. So we had an idea of how can we actually utilize the diel-south direction to access the 6,6-disubstituted cyclohexanols instead of 4,4-disubstituted ones. And we proposed that we need to have some kind of a ketene diene equivalent for this to happen. So if we have some kind of a ketene diene, we react with any kind of proper diene file, potentially we can get access to the desired 6,6-disubstituted cyclohexanols. When we looked in the literature and screened for different equivalents for the, all this idea of the ketene diene equivalent is 1,1-diheteroatom butadiene, diheteroatom substitute butadiene. The idea behind it is that we have two heteroatoms that form a heavy acetal or aminal, which upon hydrolysis will relieve the desired fragment. When we looked in the literature for the 1,1-disubstituted butadienes, the examples for the 1,1-deoxysubstituted butadienes was nearly non-existent. There is only one example of a 1,1-deoxybutadiene used in the diel-south direction to date. It came from a group of Lombardo where they used it in a diel-south direction with maleic anhydride. They have shown that it's a pretty efficient reaction. However, the yield of this reaction is pretty low, and there are no more examples of 1,1-dioxybutadienes reported to date that can be efficiently used in the synthesis. But the problem with that, as was shown by several researchers, is that this type of dynes do not like to sit in the S6 conformation that is required for the reaction to take place efficiently. Because of a significant steric interaction between the methoxy group and the CH on the hydrogen on the fourth position of the diene, we have significant steric interaction that prevents the diene to adopt the S6 conformation that's required for the reaction. Brassard's diene, that's the closest equivalent to this type of diene, also was shown to proceed mostly, to take part mostly in the aldyl type additions rather than actual Diels-Sauder reactions. So we envision how can we overcome the significant steric interactions. And we propose that if we use, instead of oxygen, we have an amine on the first position. We have a significantly more reactive diene that was shown previously in our group by the synthesis of dimethylamine and siloxane. And maybe this more reactive diene will overcome this steric hindrance and will allow us to get the desired cyclohexene, which upon hydrolysis will relieve the same 6-disubstituted cyclohexanone product. So with this in mind, we proceeded further to the actual synthesis of this type of diene. So we developed a procedure to synthesize this type of dyne, starting from acrylyl chloride, just treating them with dialkylamine followed by methylation and deprotonation of a strong base, sodium HMDS, gave rise to the desired dialkylamine methoxybutadienes in a good yield, in 4 steps, as a nice yellow to colorless oils that can be stored indefinitely undamaged. However, with these oils in hand, we tried the reaction with metachlorine, but all the reactions that we tried in our lab did not proceed for a Diels-Sauder pathway. The only products we were able to get were from vinylogous aldyl addition type pathways. No Diels-Sauder adduct was seen in the NMR. So what we proposed is we still have the same strong repulsion between the methoxy group and the CH, the hydrogen of the 4th carbon of the diene. So at this point we had an idea of, okay, if we can overcome at least a bit this repulsion, potentially our diene can still be reactive for the desired Diels-Sauder reaction. So we proposed to bind together oxygen atom and a nitrogen atom in the form of oxazoridine. This way we have significantly less sterics compared to the free methoxy group. At the same time we have still the doubly activated butadiene, but potentially should have higher activity in the Diels-Sauder reaction. So again, we developed a synthesis of these types of dynes, starting again from acrylyl chloride, just treating this time with ethanol amine, followed by methanol cyclization to give oxazoridine 8, which upon methylation and treatment with a strong base, sodium HMDS, gave rise to the desired oxazoline butadiene 6 in a high yield as a stable, colorless oil that can be stored indefinitely at room temperature under nitrogen. With this dyne in hand, we tried the Diels-Sauder reaction with metachlorine, and to our delight, just upon heating our dyne 6 with metachlorine in toluene, within 6 hours we saw complete conversion of our dyne to the desired cyclohexene 10. Upon aqueous hydrolysis with aqueous HCl, we were able to produce the desired 6-disubstituted cyclohexanone 11, albeit in a lower yield, around 40%. After some optimization, we found out that the hydrolysis step is actually one of the most yield determining steps, and by switching conditions to other ones, using oxalic acid in a water THF mixture, we were able to produce the desired cyclohexanone 11 in 70% yield. So with this good result in hand, we proceeded further to see the scope of reactivity of our dyne. Know that. To our great delight, our dyne reacts very efficiently with different acronyms. Methylchlorine, butylchlorine, ethylchlorine, they all react very well with our dyne, giving rise, after hydrolysis, to the corresponding cyclohexanones in good yield. It's pretty sad, but bromochlorine proved to be too reactive with our dyne, and all attempts to involve it in the Diels-Sauder reaction with our dyne resulted only in a polymerized material. Cyclic aldehyde, to our delight, reacted efficiently with our dyne to give rise to the corresponding cyclohexene 13 in a good yield. Free dimethyl acrylene did not give any kind of Diels-Sauder addition product under any conditions, even under prolonged heating. Our regular dienophiles such as methylvinyl ketone, acrylonitrile, methyl acrylate, and others react pretty smoothly with our dyne to give rise to corresponding cyclohexanones in high yields. It's significant to note that citraconic anhydride and 2,6-dimethylbenzoquinone reacted with our dyne to produce the corresponding bicyclic products as a single diastereomere. That proves that our dyne is actually acting in a diffuse outer fashion, not in a stepwise addition manner. With these good results in hand, we wanted to explore our types of substrates. And very soon we found out that nitroalkenes proved to be very efficient substrates for a diffuse outer reaction with iodine. Just upon treating our solution of iodine 6 in benzene with nitroalkene, within minutes we saw complete conversion of iodine to the desired cyclohexene 16, which upon hydrolysis under optimized conditions gave rise to the corresponding alpha nitroketones in high yields. So we have shown that different substituted nitrostyrenes as well as substituted aromatic nitroalkenes with naphthyl groups or with heterocycles react efficiently with iodine, giving rise after hydrolysis to a corresponding alpha nitroketones in good yields. Aliphatic substituted nitroalkenes proved to be a bit less reactive than aromatic nitroalkenes. However, they still gave rise to a corresponding product. One of my favorite examples is the nitroalkene derived from the cyclohexanone. It was able to react efficiently with iodine, producing upon hydrolysis the spirocyclohexanone in a high yield, showing that this type of reaction can be efficiently used to produce the spirocyclic compounds. With these good results in hand, we wanted to expand the